Okay, so last time we looked at displacement, velocity, and acceleration, and we started to look at plots, but today we're going to spend a little more time with that. And these plots can be a little tricky, so they take some practice getting used to. But let's see what we can do. So the plot or graph visualizes how one variable changes with respect to another. In kinematics, almost always time is going to be on our x-axis, the horizontal axis. So we're going to be looking as we go through time, what happens to our position, our velocity, and our acceleration. And it's important to remember that as we look at plots. Think like, just make yourself stop and say, okay, at this point in time, my velocity is this. Um, and that'll help you understand what that plot is actually telling us. One of the things we have to pay attention to is the slope of these plots. And that's going to tell us the rate of change, okay? So if we look at our definitions for, this is average velocity, right? Our displacement over time. Acceleration is our change in velocity over time. Well, slope is the rate of change of something. And so a plot of, if we look at a plot of position, and we look at the slope, we're getting the rate of change of position, and that's going to give us our velocity. So this is a lot easier to see visually, so let's move on and look at our plot here. So we look at this plot here, and we think to ourselves, this is the first step when we do these. Okay, I've got time on the bottom, this is velocity over here. So at time equals 0, I'm not moving, right? At time equals 1, I'm moving what? About 10-ish, 10 meters per second. That means I'm moving forward, right? I'm moving in the positive direction. What happens after 2 seconds? Well, not my position, but my velocity has changed. And now I'm moving a lot faster, right? So you can see we're accelerating. Our velocity is going from 0 to 10 to 20 to 22 or whatever those numbers are, right? So here, this plot shows us acceleration, and that's what this slope is. The slope is going up. That means we have a positive slope. That means we're going to have a positive acceleration. Our velocity is getting faster. And so that slope here is delta V over delta T. Hey, that looks like that, right? So that's our acceleration. And we can figure that acceleration by saying in 2 seconds from here to there, I'm going 12 meters per second faster. And it's taking me 2 seconds. So that's 12 divided by 2. And that gives me 6 meters per second squared, or 6 meters per second per second. Every second, I'm going 6 meters per second faster than I was the previous one. So let's do a little test here. And here we've got a position. Again, stop and say, okay, this is position over here. So this is saying, what is this dog doing? I'm starting at 0. Okay, he's moving in the positive direction, right? Because by the time we get to the end, he's gone 250 meters in that positive direction. So keep that in mind. Time 0, he sees a squirrel, chases in a straight line. So even though you look at this and you think, oh, he's got a curvy line, he's running, swervy. He's not. This is all in the X direction, right? It's his position in the X direction. We're not looking at a map of where he's gone, okay? So at 10 seconds, he's 20 meters in that straight line. At 30 seconds, he's gone 150 meters in that straight line. So let's test this out. What's the dog's velocity at 0 seconds? Well, velocity is the slope of your position graph, right? How fast is he moving from position to position? And so here, if we took the slope of that line right there, we'd find that at exactly 0, instantaneously, he's not moving. okay, roughly. So the slope of the line right here is almost flat, which means he's not accelerating in a very much way, okay? In other words, his position isn't changing. If that line stayed flat, that would mean the dog was staying in the same place. Its velocity would be 0. How far away is the tree that the squirrel climbed up to? Let's say he chases him until he climbs up that tree. This is just position. We're just looking at position here, right? So how far away is he? Well, he runs and he runs. He gets to 100 meters. He gets to 150 meters. He gets to 250 meters. And he gets to about 300 meters. That's how far away he ran. That's the total change in position. When is it running the fastest? In other words, when is its velocity here the highest? Well, remember this, the slope of the line of position is equal to velocity. So we're looking for the biggest slope, right? So the slope is very small here, gets bigger here, it's big here, and then it starts to get smaller here, right? Our slope is kind of evening out, and the dog slows down and barks at the poor squirrel. So right in here is actually where we have the highest velocity. In other words, that's where our position is changing the most, right? From here to there, the dog moves a long way. Its velocity is high. So around there, really that whole straight line there, he has the same velocity, and that's the highest velocity. When is acceleration the highest? Now that's a little trickier. There we actually have to look at the curve of the line. A downward curve like this means the slope is getting smaller, right? And if slope is velocity, our velocity is high here, velocity is a little lower there, velocity is a lot lower there, right? So he's accelerating or decelerating here. His velocity is getting slower. In here, the velocity is getting faster, right? He's going 0 meters per second, and then, whatever, a little bit faster, and a little bit faster until he gets to his high speed. So his acceleration is happening here, and we can see that on a position plot as this upward curve. That means that he's accelerating in a positive direction. And finally, what is the average velocity? You might say, how could I figure that out? That's, I'd have to find the velocity at all of these different points and average them. I don't even know how to do that, but it's much easier than that, okay? Average velocity is always easier. You find your finishing point, you find your starting point. That's how far he's traveled, right? And you divide by the time traveled, right? So if I go to Chicago and it takes me 2 hours to go those 120 miles, it doesn't matter whether I'm going slow or fast at the beginning or change speed or stay constant. All that matters is I went 120 miles. It took me 2 hours, and that gives me my velocity. So here we've gone 300 meters in about 50 seconds. And so we get 6 meters per second. That's our average velocity. So we're always moving forward, so our velocity is always going to be positive. Well, our velocity here is about 0. Our velocity is speeding up along here. So let's say our velocity is there, and it's a little bit higher there. And then about at 30 seconds, it's going to be its peak, right? And it stays at that peak for a while. The velocity goes like that. So for a while, we're going the same velocity. And then if you remember, our slope gets smaller and smaller and really gets back down to 0 here. So he's still moving forward. It's not a negative velocity, but it's less than it was before. So we can say, okay, so we're kind of creeping back down to 0. So our plot looks, in my shaky hand, oh geez, this is terrible, something like this. Like that. So that's the change in velocity over time. Now, acceleration's a little trickier. We're gonna draw. He is actually accelerating negatively because at some points his speed is getting slower. So let's call this 0, right? Initially, he's accelerating positive. Our curvature is upward. So from about 0 to 20, we have a positive acceleration here. Then from 20 to 30, his velocity here is the same as his velocity there, is the same as his velocity there. That means he's actually, I'm going to change colors here. We'll do this like that. For that middle section, his acceleration is 0. His velocity is staying the same. And then for the final section here, he's slowing down, and we call that a negative acceleration. Okay, so if he's moving 20 meters per second, say here, and 10 meters per second there, and 0 meters per second there, he's actually slowing down. His velocity is getting lower, and so that's a negative acceleration. So that's what the plots of velocity and acceleration would look like.